going to be my exam from last year, all that stuff. So obviously it won't be the same as your exam, but hopefully the process of it will be the same. Okay, so the first thing is ranking in order of acidity. See if you can just go through these. We did this during a little, not the same thing, but so see if we can rank those. So which one do you think would be most acidic out of all? This one? Why? Yeah, exactly. So do you remember the rule, the closer they are together, the more acidic? Because actually if you look at this hydrogen, it can resonate here to there. So it has like a full 3 resonances. So that's going to be your most acidic number 1. What about least acidic? Why would it be the point? Yeah, exactly. We only have this one group. This was, I think he tried to trick us with this one because he wanted us to, yeah, exactly. He wanted us to think, oh, well, maybe that's just an oxygen, or if you like just glance at it. So this is going to be your least acidic. Then what about out of these? Exactly. Because of the exact rule they were talking about before. This only has 1 carbon in between, whereas that has 2 carbons. On my exam, there's 1 on acidity, 1 on basicity, so I imagine you're going to miss one of those. So I would definitely look at something like that. Okay, so the next one is rank in order of boiling. This one's just knowing your amines and your alcohols and ethers. Yeah. So which one do you think would have the highest one? Yeah, exactly. I mean, your nitrogen is 2 hydrogens right there. And then it also has that lone pair on top of it. So this is actually going to be your highest one. But what about your lowest one? So why would you say the ether first? Okay. And are you still with secondary meat or?
Well, I'm not sure whether, because that one.
Yeah. So which one do you think would be, if you just have a whole solution of this in it, are you going to have any hydrogen bonding? Are you not going to have hydrogen? So this is actually going to be our lowest one. So out of the last 2 then, though, which one is going to have the higher one? Yeah, well, why would it be the alcohol? Yeah. And this oxygen's more electronegative. Has a larger dipole. So this one obviously has to be our last one. So I could see a problem like this on there. Might make it a little more difficult. Actually, this is your
Like it wasn't sourced last year.
exactly. He's just like, well, it's talking more, right? So like, yeah, it's gonna get. He tries out really, really hard. So yeah, you should just give it. Yeah, I'll be like, I think they're all gonna fail. You should probably just give this. He'll be like,
They probably
oh, yeah.
will fail anyway.
It's only what he could get.
They
Okay, so of these three, we want to know, will it isolate as a single name numeric, or will it, yeah, going all the way back. So, the first, do you think, what's the rules behind forming a single name? Yeah, whether those lone pair of electrons will tunnel through the nitrogen. The thing is, if you look at all these, they're all positive charges. So, what about, can this one, do you think this one could be put in a single name? I have no clue. Oh, I see. If I had this, why would this not be able to be put in, or like isolated to a single name? Well, this one has a lone, well, and it has this lone pair of electrons that if you were to isolate this, that could just go and funnel through, and it forms the other. Okay, so this one, since these electrons will tunnel through, like, one might have this hydrogen coming out, but then if those electrons tunnel through, it pushes the hydrogen back. Well, that's what I'm trying, with this one, that's what I'm trying to get at. Exactly. It'll still have an enantiomer because so this one can technically be isolated. Okay, because if you look at first, you'd be like, oh, well, those hydrogens can just like go through. Actually, what happens with that is that if the hydrogen is above, if you have a Cl negative floating around, it could extract the hydrogen and get it placed back down here at the bottom. Okay, so that's why it could get wet, basically. But with this one, our hydrogens are exactly, it's just two hydrogens. So this is just going to remain as that single compound. You aren't going to have any inversion. Okay, does that make sense? A single name here basically means that if you were to form this compound, this nitrogen isn't going to undergo any sort of conversion that would make it into another. Well, the enantiomer is an enantiomer. So basically, what I'm saying is that it won't form into that mirror image by any sort of conversion. Okay, so this one won't because it's symmetrical. These two hydrogens, even if they switch spots, it's the exact same molecule. Okay. Okay, if we went to this last one, could this be isolated? You're right.
Okay. It's symmetrical.
Well, with this one though, it doesn't have another hydrogen here. So if this hydrogen gets extracted, what if it got put back on top of there, and this got pushed down instead? So what happens is that, what if this iodine came in, took that hydrogen, and then and then you have this, and the lone pair. What if this lone pair took and put the hydrogen then on top, and it inverted it to that.
Yeah, but don't you still have like your C, your like other carbons are still symmetrical, but they're attached to this. So there's no priority.
You mean like
Yeah, like that's
like over here?
like for the second, you're ranking in order of priority, right? So you have like 1 and 2, but two that are the same. So those
Oh, you mean if you like,
Yeah.
but if you switch this around, you'd still be switching the stereochemistry because this one would be going back, whereas this one would normally be coming up, but now you're pushing it back. Got it? Or like, because how this is drawn, it would look like that, right? But now, if you went and inverted that, this would be a dashed. This one will invert. Yeah. So this will not isolate into a single invert because it will invert to the other end.
Okay, that's
Okay. You see, that's why if you were sitting here taking this exam, you saw that, you'd be like, I haven't done other things too. I don't want to try to figure out this one because that's how I was. I'm just like, I don't even.
So, which ones rotate light? Like, can you just
Okay, so here. Okay, so next session I'll have ones that don't have positive charge. Actually,
Well,
I'll give you an example.
It's really not. If you show it to us,
So like I was saying with,
we're having a question every single class except for the success day and the day after.
that we said.
You know,
It's like
that's what he is in.
why?
Okay, so for this, so instead of having a positive charge on it, now I just have a lone pair. What can happen is our hydrogen can either be, because if you imagine this, the electrons are almost like up here, and then say your hydrogen is going back, like that. Okay? Did you have a realization? Hold on. Hold on. So if we look at this, okay, our hydrogen's going backwards, right? So, but the thing is that what can happen is we say, oh, well, that's a single name. But the only problem is that this lone pair, it can go and invert, go through that nitrogen, through the tunneling effect, and put this hydrogen coming out. So this is the mirror image of what we had before. Okay? So that's what I'm trying to get at.
Right, so that would go like that.
But this isn't the same as that. If it wasn't here, yes, it would be a no because we can't isolate here.
Well, why would you assume that the chlorine would just extract from nitrogen? Well, I guess.
No, even if the chlorine took this hydrogen, the thing is that it goes and takes it, but this nitrogen would still want to extract the hydrogen because we're in a real if you form HCl, HCl is going to break apart. So it's going to extract this proton anyway, and even if it put it up here, it's not going to make a difference because this lone pair is still going to be going back and forth. Okay, does that make sense? Hey, you want to understand this too. Because if it comes up on the exam, I don't want to hear about it. So this cannot be isolated as a single enantiomer because this lone pair can tunnel through and invert our stereochemistry. Okay? But oh no, I'm just going for the example on there. So if we have this though, for one, we don't have a lone pair of electrons. Two, if we were to go and extract this hydrogen off there by chlorine, this nitrogen would just take it again. Either way, we still have two hydrogens. Exactly. I mean, if you were to draw the mirror image is just exactly what this is. So you can isolate this into a single one. So that one is a yes. And this one was a no, because of what I was saying. Well, it's not.
That's what I was thinking about.
Chiral centers really
That
don't
one
have.
So what we did in class, yeah.
Wait, when did I trick you?
The carbon, yeah.
Oh, you should know.
No. But there is.
Wait, so what are you saying there? Oh, that something else could have been chiral. So like, I don't know, like this is a chiral center. Oh, and then it actually could have. I'll give you guys that. Anyway. The thing is, so okay, with that, because you got to think about. Here, I'll draw both of them. You got to think about what's happening. So, if we just have this, because isn't this a chiral center? Okay, so if we're just looking at this single compound, we want to say, okay, if this was to invert, if these two hydrogens, say, switched positions, and we went and made this into that, let me just flip. No.
When the you have them going back.
Yeah, it would be those two. This instead of going back would be kind of forward. I'm doing the same thing. Yeah, if you were to just wait, if you were to just flip this, if you were to flip this, it's the exact same thing.
That's why I was confused. I was like, there's no chiral, like, you can't separate it. Although, well, yeah,
It doesn't have another.
right. Either R or S.
Yeah, so this can be isolated into a single group.
Okay.
Okay. And then, is this one? No, this one's pretty straightforward. There's no chiral spots. But with that one, it's a little bit different. What's happening with there? So you have this. What's happening here is that our I negative that's over here, because when you just look at this, would you say it would isolate into a single thing? No, it wouldn't. And the reason for that is if you were to extract this hydrogen and put those electrons back up, well, yeah, for one, I mean, you're putting a lone pair on there, it's a tunnel, but two, what happens is that this nitrogen, now that you put that positive charge to it, you have that lone pair. It can either attack up here or attack down there, putting the hydrogen either up here or down below. So if you look at both these compounds, so these are the two things you can get. Can you isolate this into a single one? No, because you're getting both of these. That proton is basically, it's almost like the proton. Okay, because it's like, it's basically going through and going up here instead of being down here. Okay, so basically the main things that you should remember from this is that if you have a nitrogen with positive charge and has the two symmetrical, in this case hydrogens on it, really it doesn't matter because they're symmetrical. It's not going to matter which way you put it. And then, Well, yeah, that's
Actually, or
exactly, because if this was, say, hydrogen right here, now it can be isolated because this is the exact same thing. If you were to switch those around, it would be the same thing. So then the thing to remember with this one is, if you have a hydrogen, some other group on that hydrogen, okay, this hydrogen can get extracted, it can be put in this position and that can be pushed down to right there. And now you have two different compounds. You have this is all happening in just one little solution. Okay, you're not really doing a reaction. It's just this is what the molecule is constantly doing. It's constantly switching between these two different things. Okay, and that's what he's talking about right here. This one, no, it'll stay like that. What about this? And why do you say that?
That
Because it
and
can't.
that's like four different groups.
Yeah, exactly. For all those reasons. I mean, for one, yeah, there's no hydrogens. You're not going to invert it. You're not going to switch it around. To take a methyl group off there, you're not going to do that. So this isn't going to go and invert in any way. It doesn't have a lone pair of electrons. Okay? So this can be isolated into a single.
Give us like because that would be boring.
I would hope not. I can't guarantee it, because who knows what it would do. Yeah, I don't. What? Oh no, I like it. I mean,
It's just a tough, like,
yeah, I mean,
oh, that's tough.
that's what I was gonna say. I'm like, well, I guess you could say possible, but that would be weird. Okay, so see if you can figure out this. Well, if you added ammonia, where's it going to add? It's going to add to this carbon, right? You can't, you have an extra carbon. So what do you want the nitrile to look like? You want NaCN? You want KCN? Yeah, just... Okay, so KCN. And then what else do you have to add? Not, probably not in this case. You wouldn't have to put it. Yeah, nothing. Okay, and then with H2O, and then workup. Wait, what?
I was using the H2O as the flavor, but
Oh, H2O for workup?
what would that like?
Usually, you use H plus in workup just because if you have, say, this floating around and like a carboxylic acid, workup's typically because you want to make that into a carboxylic acid. So you put and when you usually always writes H plus H2O. When I wrote this in my page,
Wait, H2O.
yeah, I think H2O would just be more of your salt. I don't think, I never usually put H2O when I did lithium hydride, so you wouldn't have to worry about it. Yeah. You wouldn't need it, but if you want to add it, I don't think. Does everyone? So this one was relatively straightforward. If mechanism-wise, because you might CN comes in, takes that position, picks out the iodine, so now you're left with that. And then this just gets reduced. What's going to happen? Double bonds going to triple bonds. Yeah, exactly. It's just going to basically add these hydrogens to both the carbon and which, well, it's going to make it into a double bond, then it's going to reduce it even more. That's the mechanism that's kind of not understood. Okay, what about this? I don't know. You only have to write the product. You don't have to write the product. Wait, what was the reagent for the CL? SOCl.
Oh yeah, you're right. Okay, then it cleaves the oxygen.
Wait. You guys remember? Well, this is not my thing. What this actually does is it adds alpha to the group.
So that's the HTC.
Yeah. Yes, exactly. So I was hoping that, you know, I remember. No, just kidding. You're expecting too much. Okay. Is everyone okay with this? It's just, you just gotta go over your reaction. They're horrible. This one's a trick question. I'll give you that. Ooh. Hey, what do you think? What's your going on? What do you think? Yeah, excess. So how does that help me? So was it? I'm going to tell you that I got this one wrong on my thing. Here's what I put. I got 1 point out of 3 because this was the one he was trying to trick us.
So the HCF that you got.
I had to look it up in the book last year, so I had to look. What charge does MgBr have on? What charge does the methyl have on? Does it attack the carbon? How much does it have to? Well, this is a very good nucleophile though. What were you going to say?
No.
She's got it.
Like I said,
I'll give you a clue. It's not attacking that. What's the most acidic spot on this carbon? Then you do workup, and it gives you that. what's happening is that it's producing methane. You have, really this is probably one of those mistake reactions. They probably like, can do that.
So
Um,
it's because of excess.
The excess is to make you think it's going to attack the turbo. You see, that's how. So what's happening here is this is an extremely good nucleophile. If you had OH minus, which is also a very good nucleophile in here, it's going to attack that hydrogen because that's the most acidic spot. It's going to want to put that negative charge in. Okay? It's not going to come in and attack here because this is the most likely position to attack. That's why I gave you 1 point because, oh, well, you might get some of that other thing. But the major product of this is that.
So the methyl attacks the
Yeah. So really, when you put a Grignard on, it's almost like that. Okay, so what?
Because like didn't you use like the two equivalents were supposed to like attack pipes or something?
No, that's exactly what you should be thinking. But if this was like an aldehyde, then yeah, by all means, like attack the. But it's a carboxylic acid, so. I'm telling you, this was on our exam. We never. Yeah, this is a half play. So, what? Well, okay. So you take that off, but now you're doing your workup. So that's when it goes back.
It was a quantum ego.
Yeah, if this was say, I don't know, and like I said, aldehyde or ketone or like acyl chloride, then you'll get something different. It'll attack that carbonyl position. Oh, yeah, he could easily. Yeah, it does what you immediately think it should do. But this doesn't do what you think it should do. It didn't do what I thought it should do.
Or reason why like
Because this is your more favorite spot because this is a lot more acidic. If you have a really good nucleophile and you have this hydrogen that just is calling to be pulled off, this is going to come in and take that rather than
is it because that carbon less positive like that
yeah. So this one's pulling electron density out, like you said, giving that more positive charge here. But the thing is that yeah, that can then donate in. So really, it's this constant kind of shift. Okay. Yes, that's a trick. I'm sorry, but that's what they'll do to you. What about the next one? And yeah, and why would that work? It's a better question.
I can do the heat thing, right? And then
Wait,
the
can
electrons,
this?
the double bond will attack those CH3s.
Wait, you mean this will form an enolane?
No. We'll just say the electrons in that
We'll
double
just say that.
will attack the CH3.
What's really happening here is this CH3 is coming up, taking that. This is going and taking the hydrogen off of say water. Usually you'd probably add acid here. And it kicks in our H plus. And it puts it then in this position. So it adds this CH3 over here, but then it puts that H plus over there. It's really, say first though, you went and you attack that position, this could bump that up here and put that negative charge in there. So it's stable. This is fine. Because now if we did that, we'd form CH3 here, we'd go like that. We'd have a negative charge next. Oxygen likes that. Fine. But then what happens is this is going to come down and push this double bond out and pick up our acid in the second step. Okay.
So you have like an excess of that first compound. Would you expect to add a CH3?
You mean at here?
Yeah.
But say if we added it here, that would push those electrons there from where they're going.
Well, would you still like that one? Second.
Oh, you mean like it attacks here and this comes in and takes CH3 out? Well, but this CH3 is a negative charge.
Makes sense.
So, it's all of this is. Aren't you taking advanced organic chem? Good question. I don't know.
But elected.
I was considering. Yeah, that's what we just talked about whenever he's passing college or whatever. Because it's his first year. So, usually Sean. Yeah, exactly. That's why I'm entertaining it. But he's teaching it nicely. True. Unless you want to go into organics. I mean, it's an interesting subject. Okay, is everyone okay with this? Accepting of it? Okay. Yeah. Okay. Don't worry, I got it. Look at what you have down here. Exactly. So we have this, and then we have our butyl, which is going to come in, extract that hydrogen, and form then our enol. Okay, now I'm good.
First thing you see is O, which is from the T
Oh.
and then it's okay.
Okay. Wait, oh? Okay. Okay, so, what do we do now? Wait, all I heard was being Bob. So, what about that part? With what? So,
Wait, where's that?
whoa! Wait. Typically it's... Well, actually oxygen with negative charge is relatively stable, but there's a more stable for it. If it came down and kicked that out, that's more stable for it than staying. It's all the equilibrium principle. Because it can go the other way, sir. But, I mean, that's why he always showed you like PKs, like, oh, which one's going to be higher?
I never remember those.
Yeah, try to remember those.
They're horrible.
He might, well, I will. So, okay, so if we, what we're doing is our oxygen is collapsing, it's kicking out this double bond and attacking our carbonyl. required.
Well, okay, do you use the second, is the second equivalent like deprotein to the second? Like alpha.
What do you mean, like?
I don't know, because it'll form that, you're gonna pop those electrons out.
Like that?
Yeah, so. Right down.
Just something noisy.
Oh, yeah.
Oh boy, okay. So, if we did do this, so, okay, we get something, we get that. And now, do we have to collapse that? Are we even able to collapse that? No. So what are we going to do?
Yeah, there's a hydrogen.
Um,
To check it.
well, this one, it already had an O- on it. But what's going to happen, though, is it is going to extract the hydrogen from this. It's going to take that hydrogen, and now we get back, or we get another O-. It's not a catalyst, though, because we're adding both of these in. So it is using that one of them.
What's the purpose of that?
It's the start of it. Because once it starts this process where it takes the hydrogen, now we can get out the. So we're going to end up with that, and then this is going to form. So we're going to get. Yeah, I know. And that's the worst part is when something like this gets put on your exam and you're constantly drawing all this stuff. Like, exactly. And then you end up missing a methyl group. It's like, oh.
Yeah.
Okay, we're not done yet. So we have this OH here.
I'm just trying to figure out
Yeah,
how that
no,
would
you're
work
right.
exactly though. Usually there would be like the carbon. Wait.
Uh,
There's only one hydrogen.
I'm here. Well, this still wouldn't form a double bond though, because then we'd have. It's really hard to kick out a hydrogen too, if it's attached to a carbon. Oh, you mean if this? Well, no, that's actually what happens. This is going to end up somehow leaving. And then exactly what you're saying, it's going to condense. What type of solution
You have
is
to take
this?
another. You have to take another alpha.
Exactly. Is this a basic or is this an acidic solution? It's a basic solution. Can this lead?
Yeah, but can't you extract the two? There's that one and there's that one. So you get two products.
Okay. Is there a hydrogen right there?
Yeah.
1, 2, 3, 4. Yeah, there's even actually if there was a hydrogen there, would be more stable putting the double bond there or there. Wait, right or left? Left because it's actually conjugated back with that oxygen. So what we're gonna. Well, this oxygen's gonna be gone. So what's happening is it's leaving. It takes the hydrogen and it's going to kick out that OH. It's a basic solution, so it's going to condense even further. Even if you haven't seen it lately, you got to recall. Landlords love them. No, he said it's the stable residence, so landlords love them to stay. Okay, bad joke. Anyway, what? So, after we get home, don't worry, I wouldn't get this major. I believe to be a
You guys know the benzene mix.
I don't even want to know. They'd be throwing benzene at me then, and I'd be dead. What? Chemistry major, do you understand how this works? I'm just kidding. No, that's what Orgo is. Basically drones. Here, I'm gonna go through it, recap it. Okay, so this would be, yeah, more than 22. First thing that happens, our detoxy group is going to come in, it's going to extract the alpha hydrogen, going down, forming a phenol, and then it's going to put the negative charge in this oxygen, so we're going to get this, okay? So we have this now. We have a carbonyl group that's just waiting to get attacked, so it has an oxygen bond. So this oxygen's going to collapse. Where else would this attack? I mean, technically it could go and attack this hydrogen, but that wouldn't help us at all. So we're going to have it come up, it's going to attack this part, and then now we're going to get this. It's probably confusing going from here to here just because now you got to redraw these structures, how they fit together. So we get this. Now what needs to happen is, okay, well, we have this turf detox group. And so this oxygen is going to go, it's going to extract that hydrogen. So now we're going to get a nice OH. Okay, everything's cool, it's stable. We're in a very basic solution because of this turf detoxy. You have these bases everywhere. So what's going to happen from here then is that we can then abstract another alpha hydrogen, alpha to this hydroxy. So it's going to come in, it's going to attack that hydrogen, and now we're going to get a condensation reaction. I don't know if during class you've gone over this specifically, this part. I don't know if it's got there yet. I believe this is actually 22, but it's further condensation. So that would go down, form this double bond. It's kicking out this OH. It's basically kicking out
There's a situation where I would choose to regulate, I would choose to attack the original compound and not replace.
Oh, I see.
Or is it just because of the proportions? I mean, in this one, I guess, like, obviously, it's said number one. I don't know. Or, like, I guess you get a picture.
The thing with this one is that this carbon group is a lot harder to attack than that carbon. Because for one, this is in a ring, and this one only has, it's just an aldehyde, it only has a hydrogen. So it's a lot easier. That's why I would imagine. Yeah. And probably another reason why I put the CH3 here is because if you put a hydrogen there, I could go and put the double bond right here. Granted, it wouldn't be probably as stable as this hydrogen group, but forming phenol right.
Is there any compound that we should like watch out for? But I don't know. I feel like you would put something there that we should attack. Or
I think you'll be fine. The only time it usually tricks you with that is when you put solvents in there and you don't realize it's a solvent. You start attacking. I know who does that. So it's the only thing I would watch out for if something looks like, oh, this is actually probably solvent. So, keep that going. You wouldn't, you wouldn't see so.
What was the one that was just salt?
But, for the ether, with the oxygen and then the two carbon.
Yeah.
Yeah, because wasn't that the one you found? Was it THS? That's right. there's some really long carbon chain. Typically, it's going to be some sort of salt because it's not really going to want to interact. But once you start throwing oxygen to nitrogen to that kind of stuff, it's really hot. Oh, that one, it had aluminum hydride, then it had blah blah blah, a whole huge group coming off. Yeah, so how do you think this one would react? What do you think it would do? And it took, not the turd, not the one with the turd. Right. This one had some long, just garbage. That's what I think. That it acts basically the same way as this, but because this is just a bunch of crap that basically keeps it from going and like putting it somewhere where you don't want it. Basically, this will just stick it out.
That's a weaker.
Yeah. Okay. Is this problem?
So, or,
Yeah. Beautiful. Look at that. It's abstract. Enjoy.
I think this whole test
That can't be like what it
Can't really. What? Yeah, this one's like 100. Yours is 100. I don't know how many questions would be on yours. On ours, there were like, there were probably 10 of the box questions, and there were, I think, 5 mechanisms.
here.
Yeah, why not?
I'll give you a clue. This is going to form multiple products. What's going to be your nature product? That's helpful. Thank you. I'm positive. What's going to happen first? Attack by or attack of?
Attack of. Attack. That's
Attack
gonna
of the
attack the
nitrogen.
nitrogen. Oh wait, no, you're right. Yeah.
What's it going to do? Yeah, because nitrogen on this whole thing is the only thing that's going to. What's it going to do though? I want to redraw that. So it gets this. It has positive charge there. Yeah, so now we have this salt. So what would happen next? What does He2O do? Do you guys remember this kind of reaction though? If you're forming the salt, what is this good at leaving? Yes, no, maybe, no. Give you a clue. No. Yeah. Very nice. Which H is it? Which H's can it? Wait, you mean just that one? Wait, I thought it was only 2 products. I was wrong. It's more than that. How many H's can it take off? Or where does the carbon have to be as compared to the carbon that's attached to length? Yeah, it has to be the beta carbon. So we have a beta carbon here. Where are they? There and there, right? Whoa. I feel like you're the only one that understands.
I'm confused. So which one's alpha? Alpha to the nitrogen or alpha to the?
It's gonna be 2 away from the nitrogen. So 1, 2, 1.
Oh.
So H2 H-E. Oh my gosh, that was really bad. I didn't mean that. I didn't realize what I said. Okay, so He2O. What's it gonna do? It's a long day. Yeah, it's gonna extract the H's. So how many different products do we do? So we'll call this A. So what is A gonna look like?
It's a double bond, like, and then the nitrogen.
So this hydrogen is gonna be taken off before that double bond. And then what else can happen? Or it could take off this one, put in double bond there. Or it could take off that one, put in double bond there. So we'll do A first. Wait, just look at it. Take a little bit of time. I'm assuming this probably isn't like covalently bonded. Yeah. The Yeah, the heat just kind of helps the reaction. So if we did A, our first product, we got to look at, okay, well, so our double bond's forming here, right? So let's just draw that. And then what do we have coming off of it? So we have a methyl group, an ethyl group, and then over here, this hydrogen's gone. So, and how is this going to lay down? How is this going to, yeah, like, because what if I put this there, but what if it actually goes there? Which direction is it going to go? How, well, is it going to be up or down? So it would be like that. Okay, so here's the reason why, though. It has to be anti-periplane. This hydrogen has to be down here for that to be kept off. So it comes up and it pushes that out. No, this is right. So what do I have to do is I have to put this hydrogen down here, so I have to flip this. So now this group is then going to be coming out this way. So the groups that are coming out in this direction are going to go in the same spot. We're going to go in the same direction. And then these two are going to be going backwards, so they're going to fly flat. So basically you got to flip it and then smush it down. I hope not. Hey, well that was like during class when you told me to teach it, and I seen up there, and everyone's throwing out like random things and compounds, and like, I don't know what you guys are talking about. And then the kid in the front, Raga, he was trying to mess with me, and so he's like, oh, it's blah blah blah, and I'm like, why don't you come write it? Like, and so he's just like, no. I'm like, what are you talking about? Like, no. Like, I'm fine. And then I found out he was trying to listen, so. But then I was going to tell Mooney, oh, I think you should make it more just the names on it. Like names. Sure, I didn't.
Oh,
That was actually horrible.
I feel like that's not funny.
No, I was going to do that, just tell them to make like a special one.
Can you go over that?
That's fine.
No. Remember, it's not people.
Sure, are you?
Like today's Friday, so and on the last day, like I was.
Oh, the names? Okay.
And all.
I'll try to teach them
No,
kind of like,
I feel like
yeah, if I have time to try to look at all the names to make sure I like put it on there so I can point them out, I'll try to do that. I would just, when you study and you go through your notes and go through the reactions, he always writes the names on the board. Just remember what names he's putting. Oh, I know. That's why when I saw it, I'm like, oh, that's pretty bad. Never did that. Wait, no, really, do you understand what's going on? Because I'll go through. So really, well, okay, so real quick, really this is going to be, it's going to be flipped, so your H is going to have to be down there. If we flip this around, this group's coming out, and then that one's going back. So with B, I'm going to draw the double bond. We have a methyl group coming off, and then we have our other CH3 group, and then does this change at all? No, this is going to be, we're not extracting that hydrogen, so this is just going to be like that, and then our H is like that. Yeah, exactly. The double bonds forming right here. Why does it flip like this? Because it has to be, if this hydrogen's extracted, it has to go like that and like that. It has to be like, and then this just basically gets squished down from there, so the two coming out just get pushed down on the same side. Then there's the other. Okay. Oh no, C, just go. So C now, we have like that, right? Because it's just making this into a double bond. And then the next one, I don't have time to go through it, but write this one down and come back Friday with it. I know no one will, because I probably would myself. Is this really? Wait, was it really? It was on our exam.
Yeah.
I wonder if it gets
Not this exact problem.